Hello and welcome back to our series on SerDes Basics. In the previous video, we saw that signals are not ideal digital waveforms, but instead analog signals that must be carefully sampled at the correct time. We also introduced the idea of timing margin, voltage margin, and how clocking is generated and recovered using PLLs and CDR. And we introduced differential signaling as a key technique for maintaining signal integrity at high speeds. But this raises an important question. What else happens to the signal as it travels through the channel? In this video, we're going to explore that in more detail. We'll look at how real channels distort signals, what kinds of impairments are introduced, and why those effects limit high-speed communication. Let's start with the channel itself. As we've discussed previously, a channel might seem like a simple connection between the transmitter and receiver. This could be a wire, a PCB trace, or a cable. But at high data rates, the channel behaves very differently. Instead of acting like a perfect conductor, the channel behaves like a complex analog system that alters the signal as it passes through. This means the signal that arrives at the receiver is not the same signal that left the transmitter. To understand why, we need to look at how the channel behaves in the frequency domain. And to help illustrate some of the information in this video, we are going to use hyperlinks, a signal and power integrity tool from Siemens. For those not familiar with hyperlinks, it is a simulation tool that allows engineers to predict, analyze, and validate high-speed PCB designs before manufacturing. It helps identify issues like reflections, crosstalk, timing violations, and EMI early in the design process, reducing risk, cost, and debug time. When we transmit digital data, we are not just sending ones and zeros. We are sending waveforms that contain a wide range of frequency components. Sharp edges of waveforms require high frequency energy, while slower transitions correspond to lower frequencies. A key property of real channels is that they do not treat all frequencies equally. As frequency increases, signal attenuation also increases. High frequency components of the waveform are reduced more than low frequency components. This behavior is caused by several physical effects, including skin effect, where current concentrates near the surface of conductors at high frequencies. Dielectric loss, where energy is absorbed by the insulating material, and conductor roughness, which increases effective resistance by forcing current to follow a longer, more irregular path along the conductor surface. Hyperlinks can display the expected attenuation of a signal based on input parameters like dielectric loss, conductor roughness, trace width, and many more parameters. Because high frequencies are attenuated more strongly, the channel behaves like a low-pass filter. This means the channel is effectively limiting the bandwidth of the signal. We can plot the channel's frequency response in hyperlinks. Here we have a differential pair of a SerDes channel. You can see that signal attenuation increases as frequency increases. So what does this actually do to our signal? As high frequency content is lost, edges become slower and more gradual. Transitions become rounded instead of sharp. The waveform spreads out in time. This leads to one of the most important effects in high-speed communication, intersymbol interference, or ISI. ISI occurs when energy from one bit interferes with neighboring bits. In other words, the channel has memory. Instead of each bit being independent, the signal at any given moment is influenced by previous bits. This means that different bit patterns can produce different signal shapes. For example, alternating patterns may produce clean transitions. while long runs of identical bits may produce slow, smeared transitions. This means the receiver is no longer seeing isolated bits, but a combination of the current bit and residual energy from previous bits. ISI is one of the primary limitations of high-speed communication systems. Another important effect in real channels is reflections. Ideally, a transmission line has a constant impedance. But in practice, impedance changes can occur due to connectors, vias, and changes in trace geometry. When the impedance is not consistent, part of the signal reflects back instead of continuing forward. We can use hyperlinks to see the changes in impedance as the geometry changes along the channel. These reflections can interfere with the original signal, creating additional distortion. This often appears as ringing or delayed echoes in the waveform. Let's simulate a 1 GHz oscillating signal on this channel to see how impedance discontinuities affect the signal. We can display the positive and negative signal of the transmitter along with the differential received waveform. And on those waveforms, we can see some ringing happening. In addition to loss and reflections, signals in real systems are also affected by crosstalk, which occurs when energy from one signal couples into a nearby signal path. At high speeds, signals don't stay confined to the metal trace itself. Instead, they propagate as electromagnetic fields that extend into the surrounding space, including the dielectric material and nearby conductors. When two traces are close together, these fields can interact. There are two main coupling mechanisms: capacitive coupling, where electric fields couple between traces; inductive coupling, where magnetic fields interact due to changing currents. Crosstalk typically shows up in two forms: near-end crosstalk or next, which appears near the transmitting side; far-end crosstalk or fexed, which appears at the receiving end of the neighboring line. These effects depend on things like trace spacing, routing geometry, and the signal's rise time. We can visualize crosstalk effects by changing the separation distance between two traces. I have two traces here, and I'm going to run a simulation where one of the nets is stuck at a high voltage and the other net is oscillating. I'm then going to sweep the separation distance and see how that affects the net that is stuck high. As we can see, as I increase the separation distance between the nets, the effect of the aggressor net on my victim net starts to decrease. In addition to crosstalk, signals are also affected by noise, which introduces random variations in the signal. Noise can be thought of as unwanted disturbances added to the signal, causing the waveform to fluctuate around its ideal value. Unlike effects like ISI or reflections, which are deterministic, noise is random and unpredictable. There are several sources of noise in real systems. One of the most fundamental is thermal noise, which comes from the random motion of electrons in conductive materials. This type of noise is always present and increases with temperature. Another source is power supply noise, where fluctuations in the supply voltage couple into the signal path through the transmitter or receiver circuitry. All of these effects add unwanted variation to the signal. Let's step back and connect everything. The transmitter sends a signal with well-defined timing and shape, but as that signal travels through the channel, high-frequency components are lost. Transitions become slower, bits begin to interfere with each other, reflections and noise further distort the waveform, and by the time the signal reaches the receiver, it is significantly degraded. In this video, we've seen how loss, ISI, reflections, and noise all combine to degrade the signal. These effects reduce both timing margin and voltage margin, making it harder for the receiver to correctly recover data. But we're not done. Modern SerDes systems are designed specifically to overcome these challenges. In the next video, we're going to look at equalization techniques and how the transmitter and receiver work together to compensate for channel loss and restore signal quality.